Good morning or good afternoon. Today, what we're going to do is we're going to go over graphs of irrational functions and also simplifying radicals. Okay, so in your packet, this is page 218. And then from there, we're going to skip a few pages. We're going to go to pages 221 and 222. First things we're going to talk about is graphs of irrational functions. So remember when you take a square root of a number, you typically get an irrational number, unless that thing you're taking a square root of is a perfect square. So if you're graphing something like y equals the square root of x, you're going to have some values, many values of your y value that are irrational numbers. Okay, anytime you plug in an x value that's not a perfect square, your y value is going to be an irrational number. We call this an irrational function. Okay, now I want to relate this to what we did in chapter 5, where we did quadratics. We graphed parabolas. We graphed something in the form of y equals x squared. Here what we're doing, this graph is y equals radical x. Okay, these two are very closely related to each other. Remember what y equals x squared looks like. Okay, we would graph right here, the vertex was here. We go over 1, up 1. From there, we could go over 1, up 3. Get to 2, 4. That was that pattern of over 1, up 1, over 1, up 3, over 1, up 5. You would get your parabola. Okay, y equals rad x is very similar. Now, if we squared both sides, we get y squared equals x. Notice these two things are very similar to each other. Okay, they're actually inverses of each other. You get an inverse when you switch the x and the y. When you graph this thing, this was your x-axis, this is your y-axis. It's going to be basically the same thing. It's going to be the reflection over the line y equals x. So if we took this graph and we reflected over the line y equals x, we would get something that now looked like this, a sideways parabola. Okay, so now you'd have a point here. You could go over 1, up 1. And then from there, you go up 1 over 3, up 1 over 5, and you get something that looks like this. Now that would be the graph of this. However, this and this are not really the same. This thing's not a function, so we can't write it in terms of y in function notation where the y is by itself, where we can do this whole thing at once. If we wanted to take the square root of both sides, we'd have to do y equals positive square root of x and y equals negative square root of x. The y equals positive square root of x is this part. The y equals negative square root of x is this part. Okay, so when we graph this function, y equals square root of x, it's just the top part of the sideways parabola. Okay, and once you recognize that, you can see how this all comes together, and how this general equation, which I'm going to go back to the other page, this general equation looks a lot like your general equation for a parabola. Where you have y equals a times x minus h quantity squared plus k. Okay, now notice how these are very similar. The hk in your formula, for both of these is your vertex. This a value, just like this a value, stretches this in the vertical direction. Okay, so it's going to make it open more narrow. It just stretches it in the vertical direction. So vertical stretch or compression. Compression, if your a value is less than 1, because you're multiplying that y value by something less than 1, so it compresses or it shrinks down. Okay, and if a is greater than 0, we know the parabola opens up, and if a is greater than 0, we know we have. For this, if a is greater than 0, we know we have the top half. If a is less than 0, we know we have the bottom half. or it's the reflection over that line, that axis of symmetry. Okay. And then what else was there? There was, oh, we didn't really talk about a b value here, but if you have a b value in front of your x, like this b value in front of your x, it kind of does the opposite of what you would think. Okay. So a horizontal stretch or compression by a factor of 1 over b. For b less than 0, it's a reflection over the y-axis. Okay. We're not going to go into this too much, so I wouldn't worry too much about that, at least in this course. Okay. Now the horizontal translation and the vertical translation, you're just moving this thing. The HK tells you your new vertex. So it shifts the entire graph, but you start with the vertex. Okay. So for instance, let's say we have y equals 2 times square root of x minus 3. And then outside of your square root, you have plus 1. Your vertex is going to be 3 comma 1. Okay, so it's x minus h, x minus 3, so h is a positive 3, then plus k, plus 1. Okay, so your k value is 1. Okay, so let's look up here. If we were to graph this thing, you could make a table of values. Now notice, this is just the positive square root of x. When you take a square root of a positive number, we know we cannot take a square root of a negative number. You get something that's not a real number. When you take a positive, a square root of a positive number, you always get a positive. So it might make sense to put in 0 and then plug in perfect squares for x. So 1 is a perfect square, 4 is a perfect square, 9 is a perfect square, and 16 is a perfect square. And we can see exactly what I was telling you over here, how it's going to follow that pattern of up 1 over 1, up 1 over 3, up 1 over 5. So the same kind of pattern you have for a parabola, just in a different direction. Okay, so if we plug in x, square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3, square root of 16 is 4. So we've got 0, 0, got 1, 1, got 4, 2, got 9, 3, and we've got 16, 4, which is off the page. But you can see you've got this graph that looks like this, okay, following the pattern of up 1 over 1, up 1 over 3, up 1 over 5, up 1 over 7, and you get to this point here, 16 comma 4. Okay, so let's look at how we can graph these fairly easily, looking at a few examples. And again, we're not going to go too deep into this, so we're just going to do a few examples. Okay, so this one, we know that the square root of x looks like this. So sometimes you might want to graph your actual graph first, or the parent function first. We know that these points would be here. I'm going to graph that really lightly because I'm going to erase it when I'm done. Now this thing, that minus 4, tells you your new vertex is shifted down 4. Okay, that's your k value. Your plus k is minus 4. So my vertex is going to be, instead of at 0, 0, it's going to be at 0, negative 4. So each of these points gets shifted down 4. Or you could go down 4, 1, 2, 3, 4. There's your vertex. From there, you can follow that pattern of up 1 over 1, up 1 over 3, up 1 over 1, 2, 3, 4, 5. And this is all you're doing. You've got this graph right here. Okay, your domain is x is greater than or equal to 0, or you could say 0 to infinity. The range, okay, your y value is never less than negative 4. So your y value goes from negative 4. And notice this thing will always keep going up and up and up. So it goes all the way to infinity. Okay, just so you can see that. That was negative 4 up to infinity. Okay, now this one, notice this thing right here, the minus 4, means your h value is positive 4. Okay, so your vertex here is 4 comma 0. Everything else is the same. There's no a value, or a is 1. There's no b. There's no k. K would be 0, so you're not shifting up or down. So your parent function would be Just so I don't forget, maybe we want to erase the parent function. Sometimes you want to draw those in. But you could draw the parent function in. But now this thing's shifted 4 units to the right. Your vertex is at 4, 0. So 1, 2, 3, 4. There's the new vertex. So now you're going to follow the same pattern, up 1 over 1, up 1 from there over 3, up 1 from there. We'll go over 1, 2, 3, 4, 5. Get you to 13, comma 3. Okay, and if you want, erase your parent function. Your domain, x is always going to be bigger than 4. There's no graph over here. So domain is 4 to infinity. Y value is always greater than 0. So 0 to infinity. Okay. Y value is 0, including 0 and up to infinity. Okay. Now this one, we're shifting 3 to the left and down 1. So your new vertex is left 3, negative 3, and negative 1. Okay, now there's something a little tricky because your stretch in the vertical direction, everything is up twice as much as you thought it was going to be. Okay, so I'm going to show you how to do that. So your parent function, we don't have to draw that. I think we've got the idea. Now there's a positive number, so again, it's going to be the top half of your parabola. All of these had a positive a value. If the a was negative, it would be the bottom part. Okay, so we're going to start at negative 3, negative 1. 1, 2, 3, down 1. Okay. Now, normally we go up 1 over 1, up 1 over 3, but we're going to go up twice as much as usual. So we're going to go up 2 over 1, up 2 over 3, up 2 over 5. Okay, so we've stretched this in the vertical direction. Okay, we've got this. And then we can double check, because if you didn't quite catch that, normally it's up 1 over 1, up 1 over 3, up 1 over 5, up 1 over 7. But we're going up twice as much as we usually do for the amount we go over. So we're going to go up 2 over 1. Instead of up 1, we're going up twice as much. So 2 over 1, up 2 over 3, up 2 over 5, up 2 over 7. If this number were a 3, we'd be going up 3 over 1, up 3 over 3, up 3 over 5, up 3 over 7. Okay? Now you can always double check. It's easy enough to check this value. Plug in a negative 2 for x and see what your y should be. That pattern told us we should be at positive 1, negative 2, comma 1. So when x is negative 2, we got 3 minus 2, which is 1. Square root of 1 is 1. 1 times 2 is 2. 2 minus 1 is 1. So that works. Let's plug in the value of positive 1. The nice thing about this is, notice when we plug in a 1, we get 1 plus 3. That's a perfect square. This value over here was 1, 2, 3, 4, 5, 6. So when x is 6, 6 plus 3 is 9. We get a perfect square. Square root of 9 is 3. 3 times 2 is 6. 6 minus 1 is 5, and this should be up 5. 1, 2, 3, 4, 5. Perfect. So that works. So you can always double check your values. Let's plug in 1 just to be safe. Plug in 1. 1 plus 3 is 4. Square root of 4 is 2. 2 times 2 is 4. 4 minus 1 is 3. And that's up 3. Okay? So if you don't remember that pattern, you can always plug in values. Okay? So our domain is everything x is always greater than negative 3. And our range y is always greater than negative 1. Okay. All right, now we're going to go to simplifying radicals. We're going to page 221. Okay, I'm going to go over some examples, and then I'm actually going to do the entire worksheet. Don't feel like you have to sit here and listen to me do the whole worksheet for you. If you have questions, or if you want to just try them on your own, pause the video, and then just fast forward it and go through the ones that you maybe didn't get right and watch the explanations, okay? So a radical in simplest form where there are no square factors, okay, under the square root symbol means a positive square root. Okay, so anytime, and we were talking about this, you can't take a square root of a negative number. And anytime you take a square root of a number, you get a positive. Okay, for instance, when I take the square root of 9, I get 3 and only 3. Some students want to say, oh, the square root of 9, well, that's 3 or negative 3. Okay, that's not true. Let me give you an example. If I gave you one question, I said, tell me what the square root of 9 equals. And I give you a different question. I start with x squared equals 9, solve for x. Okay, these are two very different questions. They're not the same question. Okay, if I ask you, if I start with a positive 9 and I take the square root of it, you can't start with a positive 9, take a square root, and somehow get a negative number. Okay, that's just not mathematically correct. When you take a square root of a positive number, you always get a positive number. Now, if I started with this, I didn't tell you to take the square root. I said x squared equals 9. Solve for all x where this is true. Well, then x could either be 3 or negative 3, because 3 squared, 3 times 3 is 9. But negative 3 also works, because negative 3 quantity squared, negative 3 times negative 3 also gives you 9. So the issue that comes up is some people are taught, oh, I square root both sides. Square root this, I get x. Square root this, I get 3. Well, you're actually taking plus or minus the square root of the other side, because whenever you square something, you always get positive. But you have to remember that thing before it was squared could have been negative. So x really equals plus or minus the square root of 9. Okay? So x would equal plus or minus 3. Okay? Just notice the difference between starting with this, where your answer can only be positive, and starting with this, where your answer can be positive or negative. Okay? So if we simplify red 24, how would you do this problem? There's two methods. I've seen two methods for solving this problem. Okay, some people like to say, okay, I want to find a perfect square. Are there any perfect squares in 24? Well, there's 4, so I could say square root of 4 times square root of 6. Okay, I found a perfect square. I'm looking for my perfect squares. Remember what your perfect squares are. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 25, 36, 49, etc. Okay, so earlier in the year, we studied the perfect squares. We studied the perfect cubes. We studied all these powers that are going to make these problems easier. If you can find a perfect square that's a factor of your radical when it's a square root, okay, then that's going to be the easiest way to simplify this. So you get 2 times the square root of 6. Now, method 2. Some people are saying, oh, I've got a square root of 24. I'm just going to break it down. Square root of 2 times square root of 12. I'm going to keep breaking it down. Square root of 2 times square root of 2 times square root of 6. Okay, keep breaking it down. Square root of 2 times square root of 2 times square root of 2 times square root of 3. And since it's a square root, I'm going to look for perfect square. I'm going to look for pairs. Okay, I've got a pair of these. 2 square root of 2's gives me a regular 2. These don't have a pair, so I have to multiply those together. I get square root of 6. Okay, notice you'll get the same answer. I like this method better because it's quicker. But the problem is, sometimes if you don't know all the perfect squares, sometimes you have to do this method. Okay. So, 2 methods for solving radicals. First method, which is this method, find the perfect powers under the radical. When I say powers, I didn't say perfect squares. If it's a square root, for instance, example, if it's a square root of some number, then you're finding perfect squares that are factors of x. Okay? If it's a cube root of your number, you're finding perfect cubes. Okay. If it's a fourth root, you're finding perfect powers, things to the fourth power. Okay. And then your second method is just simply break down that radicand. We call that the radicand, the thing under the radical. Okay. And then find pairs if it's a square root. Find groups of three. So if it's a cube root, you need three of something. So find, what is it called if you've got pairs, groups of three. Groups of three of the same thing. So pairs of the same thing, groups of three of the same thing. If it's a cube root. Okay, what I mean by that, let's say I have the cube root of 24. Okay, that breaks down into cube root of 2, just like we had up here. It was a 2, a 2, a 2, and a 3, but they're cube roots. So cube root of 2, cube root of 2, cube root of 2, and a cube root of 3. But it's a cube root, so now we need 3 of something. Okay, multiplying these together, you'll get the cube root of 8. We know the cube root of 8 is 2, so this becomes a 2 times the cube root of 3. Okay. Method 1 over here, if that was the cube root of 24, you're looking for perfect cubes in 24. And hopefully you recognize 8 is a factor of 24, and 8 is a perfect cube. So you could say the cube root of 8 times the cube root of 3. So the cube root of 8, you know, is 2, so you get 2 times the cube root of 3. Okay? Okay, so if you feel good and you want to practice these problems, go ahead and do the problems on this page. Okay. I'm going to go through these problems. I'm going to go through all of them fairly quickly, but I'm going to explain them. Okay, square root of 50. Are there any perfect squares? Sure are. You could break that down into square root of 25 times square root of 2. 25 is a perfect square, so that becomes 5. 5 rad 2. Square root of 128. Okay, 128 is 64 times 2. 64 is a perfect square, so square root of 64 times the square root of 2. So that's going to be 8 rad 2. Cube root. Okay, what's a cube root in here? Well, I have a negative 54. Now remember, you can't take a square root of a negative, but you can take a cube root of a negative. Because if there's 3 of something, those 3 things, if they're all negative, then you get a negative number. Okay, so this breaks down. 27 is a perfect cube, but also negative 27 is a perfect cube. Times the cube root of 2. And since 54 is 2 times 27, negative 54 is 2 times negative 27. Cube root of negative 27 is negative 3. Think about that. Negative 3 times negative 3 is positive 9 times another negative 3 gets you negative 27. And I've got the cube root of 2. Okay. Let's find perfect squares in here. So we've got square root of 32. Well, there's a 16 in there. Square root of 16. I've got a square root of x squared. Okay, and then I've still got a square root of 2. The square root of 16 times square root of 2 gives me the 32. Square root of x squared, and there's one more x left over. I just found the perfect squares. Okay, just broke it down because square root of 16 is 4. Square root of x squared is x. And then these are left under the radical. Okay. This one, I'm going to break down that 98 into the square root of 49 times the square root of 2. Okay. And then I've got, x to the 8th is a perfect square, so I'm going to call it square root of x to the 8th. Y cubed is not, but y squared is, so square root of y squared. And then there's one more y left over, so I have a square root of y and a square root of z. And let's square root everything. This thing becomes a 7. This thing, Still a square root of 2. That doesn't simplify. Square root of x to the 8th is x to the 4th. Notice if it's a perfect square, it comes out of the radical. Square root of y squared is y. And then these two we can combine into the square root of yz. Okay, let's take everything that came out of the radical, the 7x to the 4th y, and then I'm left with the square root of 2yz in the radical. Okay. Now, over here, I've got a negative 3 on the outside. Okay, are there any powers, anything raised to the 5th inside 96? Well, it's a little contrived because the only thing to the 5th that you might probably have memorized is 2 to the 5th. And 2 to the 5th, hopefully you remember, is 32. 32 happens to be a factor of 96. Okay? We've got negative 3, and then I've got the 5th root of 32, and what's left? The 5th root of 3. 3 times 32 gives me 36, so I can break down that 5th root of 96, break down the 5th root of 96 into the 5th root of 32 times the 5th root of 3. So I've got a negative 3. Don't let that negative 3 fool you. It's already on the outside. You don't really do anything with it until you combine it with this thing that comes out of the radical. So the 5th root of 32 is a 2, and then I'm left with the 5th root of 3. Okay, so multiply these two together. You've got negative 6 times the 5th root of 3. Okay. All right, down here. So I like to take what's outside the radical, combine those. 3 times 5 gives you 15. What's in the radical, I'm just going to leave that as 2 times 4. You could multiply those to 8, but I'm looking for perfect squares. So that right there, that 4 is already a perfect square, so I'm going to leave it as 4. And I've got x cubed times another x cubed. We can call that x to the 6th. Okay. And so now we've got 15. Let's get our perfect squares. Square root of 4, square root of x to the 6th, and then a square root of 2. So we've got 15, square root of 4 is 2, square root of x to the 6th is x to the 3rd, and then I've got the square root of 2. So 15 times 2, 30x cubed times the square root of 2. Okay. Now, this one, I've got a cube root. Let's see, what do we want to do here? So I've got a cube root of 3a squared b to the 4th. Okay, so I've got a cube root of 3 with a 3a squared. There's no perfect squares in there. Then I've got the cube root of b to the 4th, which I could call the cube root of b to the 3rd. That's a perfect square. And then times the cube root of one more b. There's one b left over to give you 4 of them. And now this exponent applies to both. A cubed raised to the 1/3 is going to be, you multiply those, and I just get an a. B to the 5th raised to the 1/3, and I'm going to get a b to the 5/3. Okay, so let's see what we can simplify. This becomes a b. Let's pull that out front. B, and I've got the cube root of 3a squared b. This a I can pull out front also. Now I've got a b to the 5/3. Let's turn that into a radical. Okay. Zoom in a little bit. So that's the cube root of b to the 5th. The cube root of b to the 5th. Okay. So I've got a, b, this b, oh, that b, I already pulled that out front, right? So we don't want that twice. Right, okay. So I have the a and the b, and then I've got the cube root of 3a squared. Oh, that's under the radical, sorry. Cube root of 3a squared b, and then here I've got the cube root of b to the fifth, okay, which I can write that as the cube root of b to the third times the cube root of b squared. The reason I pulled out this is because the cube root of b squared is a perfect cube, so this just becomes another b, okay? And don't forget this term, times the cube root of 3a squared b, okay? Now I'm running out of space. That's okay. We're almost there. So this is going to be another b. A times b times another b. A times b times another b. Okay, so that took care of that a, that b, and that b. Now these I'm going to combine into one cube root. Cube root of 3a squared b cubed. 3a squared b cubed. Okay, now I've got the cube root of b cubed, so I can pull out another b. So I've got a times b times yet another b. So that's going to be ab cubed. And then what's left under the cube root is 3a squared. Okay, and I've run out of space for this one, so I'm going to do that over here on another page. Actually, I'll do it right here. Okay, so let's do this. Simplify the top and simplify the bottom. Square root of 24, well, that breaks down to the square root of 4 times the square root of 6. It's a perfect square. We're looking for perfect squares. And then square root of x to the 5th, well, that's not a perfect square. So I've got square root of x to the 4th times another x. Okay, and on the bottom, I've got 6. Well, this is just the square root of 6x cubed. Square root of 6x cubed. Okay, and let's break that apart. Okay, so this becomes, let's go over here. Square root of 4 is 2. Square root of x to the 4th is x squared. This x is under a radical, right? So we've got 2 and x squared. Then under the radical is rad 6x. In the bottom, I've got a square root of x squared. That takes out the x squared, and I'm left with 1x inside times the square root of 6x. So the square root of 6x over square root of 6x, those cancel. And I've got 2x squared over square root of x squared, 2x squared over x. One of these x's cancels, and I get 2x. Okay, so that big mess just simplifies to 2x. Okay, let's go to the next page. Some of these on the next page you probably need practice, especially some of these. These are all different types. You're going to see a bunch of these different types on your Delta Math assignment, and you'll see them on your quiz. So multiplying two binomials that include radicals. So this one and this one are similar. This one's just going to be a little bit more messy. Then when you have a radical on the bottom, what do you do there? So what do you have the radical on the bottom? And maybe you can get these to combine terms if you get them into like terms. What do you do if you divide by something, a binomial that has a radical in one of the terms or in both of the terms? And then what do you do if you have a radical in the denominator that's not a square root, but a cube root or a fourth root? Okay, so we're going to go through these 8 problems. Feel free to try them on your own and just fast forward to the ones that you think you'd like to see. Okay. So we need to FOIL. We need to multiply this out. Square root of 3 times the square root of 3 is 3. Square root of 3 times negative square root of 5, well, that's minus rad 15. This gives you plus rad 15. And then you get 5 times negative rad 5, so minus 5. Okay, these cancel. You get 3 minus 5, negative 2. That works out nicely because notice we've got a plus b times a minus b. These two terms are both the same. One has a plus, one has a minus. So when that happens, you know your two middle terms cancel out. Okay, this one over here, we're going to FOIL again. So 7 times 4 is 28. We get 28. Rad 6 times rad 2, that's going to be rad 12. That's going to be able to simplify, multiply these two, so plus 42 rad 18, and then minus 12 rad 10, and then minus 3 times 6, 18 rad 15. Let's simplify this. That breaks down into rad 4 times rad 3. 28 times rad 4 is 2. 28 times 2 is 56 rad 3. We've got plus 42. I could call that square root of 9 times square root of 2. Square root of 9 is 3. 3 times 42 is 126 rad 2. Did I do that right? 84. Yep. Okay, and then minus 12 rad 10, minus 18 rad 15. Now, none of these are like terms. All these radicals are different. Okay. Let's go to the next one. Now, when you've got a radical in the bottom, you're going to multiply by your clever form of 1, rad 3 over rad 3. So you've got 12 rad 3 over 3, or 4 rad 3. Okay. Then bring down the plus 8 rad 3. Okay. These are like terms. You have 4 rad 3s plus 8 more rad 3s, so you have a total of 12 rad 3s. Okay. Let's do this one. 4 rad 6. We can't do anything there. Minus 2 over rad 6, multiplied by rad 6 over rad 6. And plus this thing. I've got a perfect square in there, do I? 54 is 2 times 27, or 9 times the square root of 9 times 6, square root of 6. So we've got 4 rad 6 minus, we've got 2 rad 6 over 6 plus 3 rad 6. So 4 rad 6 minus 1/3 rad 6 plus 3 rad 6. Okay, so how many rad 6s do we have? Well, 4 rad 6s plus 3 rad 6s. That's 7 rad 6s minus 1/3 rad 6. 7, that would be 21/3 rad 6 minus 1/3 rad 6. Just getting common denominators. 21 over 3, yeah. So that's going to be 20/3, or 20 rad 6 over 3. Okay. Next problem. Now this is tricky. We can't just multiply top and bottom by rad 5 over rad 5, because that rad 5 would distribute to both. So even though you'd get rid of it here, you'd multiply rad 5 times a -1, and then you still have a radical. Just a different radical, but you still have a radical. So here's where we're going to do something. We multiply. Remember what happened up here in number 1. When we had rad 3 plus rad 5 and multiplied by rad 3 minus rad 5, notice what happens. The first radicals you multiply by themselves, so that radical goes away. The outers and the inners end up being the same, one positive and one negative, so those cancel out. And then your last, the rad 5 times rad 5, well, that's 2 radicals multiplied together, so that radical goes away. So we're going to use that idea. This is called multiplying by a conjugate. So we're still going to multiply by a clever form of 1, but we're going to choose it wisely. Rad 5 minus 1, if we multiply by rad 5 plus 1 on the top and the bottom, notice you're going to get a radical in the top. That's fine. Okay, 12 rad 5 plus 12. But in the bottom, you're going to FOIL. Rad 5 times rad 5 is 5. Then plus rad 5 minus rad 5. And then minus 1. These go away. And you get 12 rad 5 plus 12 all over 5 minus 1, 4. Okay, so you have two terms, both of them divided by 4, so you can simplify. That becomes 3 rad 5 plus 3. Okay. So if you understood that, try this one. You can fast forward because I'm going to do it, but try this one maybe on your own, maybe pause the video. So we're going to multiply rad 7 plus rad 2. I'm going to multiply by rad 7 minus rad 2. Okay, distribute. We've got 10 rad 7 minus 10 rad 2. And on the bottom, rad 7 times rad 7 is 7. Rad 7 times negative rad 2, so minus rad 14, and then plus rad 14. Those will go away, and then minus 2. Okay, so I've got 10 rad 7 minus 10 rad 2, all over 7 minus 2. I can divide both of these by 5, so I get 2 rad 7 minus 2 rad 2. And that's as far as you can go. Okay. And these last two, these can be really tricky. I know that we actually saw these back in chapter, what chapter was it? It was chapter 7. But when you have a radical in the bottom, but it's not a square root, it's some other kind of a root, okay? Now we can't just multiply top and bottom by the cube root of 9 over the cube root of 9. To get rid of a cube root, we need 3 of something. We need a perfect cube. And this right here is not a perfect cube, it's a perfect square. So we don't need another 9. We can think of this as 5 over the cube root of 3 times 3. We only need one more 3 down here. Because if we have 3 3's, a cube root of 3 cubed gives you 3. Cube root of 27 gives you 3. So the radical will go away if we have one more 3. So we're going to multiply by the cube root of 3 over the cube root of 3. Okay, so on the top, we've got 5 times the cube root of 3. On the bottom, I've got the cube root of 3 times 3 times 3, or the cube root of 27. So on the top, 5 times the cube root of 3 over 3, and now that radical went away. Okay. Now this one, there's a couple ways. There's a couple ways you could do this one, but let's think of it this way. Now, it's a 4th root of 49. You break down 49, 3 over the 4th root of 7 times 7. Now, to get rid of a 4th root, you need 4 a total of something. How many 7's do you have? You have 2. So you need 2 more. Okay? So that would be the 4th root of 7 times 7, and the 4th root of 7 times 7. So on the top, you've got 3 times the 4th root of 49 over 4th root of 7 times 7 times 7 times 7. 4th root of 7 to the 4th. So 3 times the 4th root of 49 over 7. Okay. Now, there is something a little tricky about that, because that's not fully simplified. And we're going to see this in a couple days. But this is a nice time to talk about this, since it came up. Okay. 4th root of 49 is not fully simplified, and here's why. 4th root of 49. You can call that 49 to the 1/4, right? Remember how you always try to get your base as small as possible? We can call this 7 squared. 49 is just 7 squared. Now, if you have a power of a power, you multiply those exponents, and you've got 7 to the 1/2. 7 to the 1/2 is just the square root of 7. This and this are equal. Okay, so you followed those steps. 4th root of 49 is 49 to the 1/4. If you turn that 49 into 7 squared, now you've got 7 squared to the 1/4. Multiply the exponents because you have a power of a power. get 2/4. Simplify it to 1/2. 7 to the 1/2 is just rad 7. This one right here is considered more simplified. Okay, we're going to actually go through that in a couple days. Okay, so that would be 3 rad 7 over 7. Okay, let's do one more like this. Feel free to go if you understand this, but if you're stuck on that, because a lot of students, if I were teaching a class, I usually get a couple more questions on this. Students are, I don't fully understand that. Let's look at this. What if I had 3 over, let's say, the 5th root of 4? Okay, now this is a 5th root. If I have a 5th root of something, what makes that 5th root go away? Well, I need a perfect number to the 5th. Okay, this right here is 3 over the 5th root of 2 times 2. I have 2 of something. I have 2 2's. I need a total of 5 to be able to get rid of this radical in the denominator. I only have 2. I need 5. So that means I need 3 more. Okay, so you can multiply top and bottom by the 5th root of 2 cubed over the 5th root of 2 cubed. Okay, so on the top, I get 3 times the 5th root, and make sure you tuck that 5 in there so it doesn't look like it's an exponent on the 3, of 2 cubed, which is 8. And on the bottom, I've got the 5th root of 2 times 2 times 2 times 2 times 2. The 5th root of 2 to the 5th. 2 to the 5th is 32, 5th root of 32. But these go away. Recognize that these go away. That's 2 to the 5th, and the entire thing is under a 5th root raised to the 1/5. When you multiply those together, you just get 1. So you just get a 2 on the bottom. Goal accomplished. 3 times the 5th root of 8 over 2. Okay? All right, hope that was helpful. And thank you for watching, and we'll catch up with you soon.